Have you ever stopped to think about how that cat video actually gets to your phone? It really does feel like magic, doesn't it? You tap a button and boom, a kitten is falling off a couch on a screen in your hand. But behind that magic is one of the most complex systems humanity has ever built. Today, we're going to pull back that curtain and see how the internet really works. So let's just start with the big question. How is it possible for a video, sitting on a server maybe thousands of miles away, to get to your screen, perfectly reassembled, in just a fraction of a second? I mean, really think about that. It's an incredible feat. And that is exactly what we're going to break down. And to do that, we've got a roadmap. First, we'll take a quick look back in time to see where this all came from. Then, we're going to map out the internet's physical structure. After that, we'll follow a single piece of data on its amazing journey, learn the essential rules of the road that keep everything in order, and finally, we'll uncover the elegant four-layer system that makes it all click. All right, let's dive in. First up, your window to the web. You know, to really get how the internet works today, you kind of have to understand where it came from. So this whole thing didn't just appear out of nowhere. It started way back in the 1960s as a US military project called ARPANET. But the real game changer came in the 70s with something called TCP/IP that became the fundamental language of the internet. Then, in 1989, the World Wide Web arrived and made it something regular people could actually use. The 2000s gave us social media and internet in our pockets, and now we're living in the era of 5G and the Internet of Things, where basically everything is connected. Okay, so that's the history. Now let's talk about what the internet physically is. That brings us to our second section, the internet's 3 regions. Believe it or not, there's a physical map to this digital world. And you can really think of its entire structure in 3 main parts. You've got the network edge, that's where you and I live. Then there's the access network, which is how we get connected. And finally, you have the network core, the massive global highway system that ties it all together. So the network edge, it's pretty simple. It's us. It's your phone, your laptop, your smart TV. We call these devices clients. But the edge also includes the other side of the conversation, the powerful computers called servers. These are usually stacked by the thousands in massive data centers, and they're what hold and serve up all the websites, videos, and information we ask for. Okay, but how does your phone talk to those servers? That's where the access network comes in. Think of it as the on-ramp to the internet superhighway. It's your home Wi-Fi, the cable running into your house, the fiber optic line, or the 5G signal your phone picks up. It's the physical link that gets you from the edge into the game. And once you're on that on-ramp, you hit the network core. This is the big one. It's the backbone of the entire internet, a mind-bogglingly complex web of highly specialized computers called routers. Their only job is to connect all these countless networks together and direct the traffic, moving data at the speed of light across the planet. All right, so we've got our map. Now for the fun part. Let's actually follow a tiny piece of that cat video as it makes its way from a server to your screen. Welcome to Section 3, a packet's incredible journey. You see, the internet does something really clever. It doesn't try to send that whole video file in one go. Instead, it uses a method called packet switching. It chops the video up into thousands of little pieces called packets. I love this analogy. Each packet is like a postcard. It has a little chunk of the overall message, and crucially, it has the destination address written on it. Now, why do this? Well, there are 2 huge advantages. First, it is wildly efficient. Because the data is in these tiny chunks, lots of different people's data can travel along the same wires at the same time, all mixed together. And second, it makes the network incredibly resilient. If one path gets clogged with traffic or a cable gets cut, the packets can just be rerouted on the fly, like your car's GPS finding a way around an accident. So inside that network core, there are 2 key jobs happening constantly: forwarding and routing. They sound similar, but they're very different. Forwarding is the local decision. A single router looks at one packet, reads the address, and in a split second decides which physical wire to send it out on. It's an immediate local choice. Routing, on the other hand, is the global plan. That's the master process of calculating the entire best path for a packet to take from its starting point to its final destination across the entire internet. So who makes this global plan? Powerful routing algorithms too. The big one you might hear about is BGP, the Border Gateway Protocol. You can think of BGP as the internet's own global GPS system. It's what allows all the huge, separate networks run by different companies like Comcast or AT&T or Verizon to talk to each other and constantly update their maps of the best ways to send traffic. When BGP has a bad day, huge chunks of the internet can literally just vanish. Okay, but for all of these different devices and networks, made by different companies all over the world, to work together, they have to agree on a set of rules. They have to speak the same language. And that brings us to Section 4, the rules of the road. These rules are called protocols, and that's really all they are, a shared understanding. Protocols are the language and the grammar of the internet. They define exactly how messages should be formatted, how they should be sent, and what to do when things go wrong. Without them, it would be total chaos. So let's meet the superstars. You've got HTTP, which is the protocol your web browser uses to ask a server for a web page. Then you have IP, the Internet Protocol. Think of it as the postal service. It's responsible for putting an address on every packet. And then there's TCP. TCP is the reliable messenger. Its job is to make sure all those little packets for your video arrive, that they're put back in the right order, and if any get lost along the way, it asks for them to be sent again. It's a total control freak, in a good way. So we have all these different protocols, each doing a very specific job. How do they work together without tripping over each other? Well, that brings us to our final section, and what might be the most elegant idea in the whole system, the 4-layer system. This is often called the TCP/IP stack, and you can think of it like, well, a stack of building blocks. At the very top, you have the application layer. That's where your apps live, your browser, your email client. Below that, the transport layer, where TCP lives, makes sure data gets there reliably. Under that, the network layer, home of IP, handles all the addressing. And at the very bottom is the link layer, the actual physical connection, like Wi-Fi or an Ethernet cable. Now here is the beautiful part. When your computer sends data, it travels down the stack. At each layer, a new digital wrapper gets added on. This is called encapsulation. So your browser's request gets wrapped up by TCP, which then gets wrapped up by IP. When the data arrives at its destination, the exact opposite happens. It travels up the stack, and each layer unwraps its part until the original data is all that's left. So why on earth does this matter? Because this layered design is what makes the internet so unbelievably flexible and robust. Each layer only has to care about its own job. It means someone can invent a brand new super fast Wi-Fi technology at the bottom layer, and your web browser at the top layer doesn't even have to know. It just works. It's genius. So let's wrap this up. What are the big things to remember? First, your data gets chopped up and travels in tiny pieces called packets. Second, all of this is governed by a shared set of rules, or protocols, that everyone agrees to use. And third, the internet isn't just one big thing. It's a massive, decentralized network of networks built from day one to be tough and to keep working, no matter what. You know, it's pretty amazing to think that this system, which started as a military experiment, now forms the backbone of our entire global society. It was designed for resilience and for growth. But with billions and billions of new devices coming online, from our cars to our refrigerators, the big question is, what's next for this incredible world-changing system?